get a general idea of what you guys want to cover today. Are there specific chapters or topics?
24.
24?
I think 24 and 25, actually.
Okay. Let's start with chapter 24. I know we covered chapter 25 yesterday. That video is up on the CLC YouTube page. I will go over some of it, but it might be better to review that video. We went pretty in depth. Let's see, chapter 24, that's carbohydrates, right?
Yeah.
Okay. I know one of the issues with that chapter, he used a lot of practical applications on the quiz. So we'll go through Dr. Cosper's notes, but I know that there are certain things that aren't covered in her notes, like the rough reaction that he did ask about. So we'll take some time to review those topics as well. Is there anything specifically from chapter 24? Or just a general overview?
As of right now, just the general
Okay.
overview.
All right. All right, so what atoms are found in carbohydrates?
Carbon, hydrogen, and oxygen.
Right, exactly. So carbon and then hydrates, think water, H2O. You should definitely know some major functions. So what would you consider the two major functions of carbohydrates?
Provide energy.
Okay, that's one. Think cellulose. What does cellulose do? Structure. Carbohydrates are definitely can be used for other functions, but those are the two major ones that you should know. What's the building block of carbohydrates? It's the smallest unit. Monosaccharides. And really, saccharides is just another term for sugar, so really this is just saying one sugar, okay? Monosaccharides can be shown in two different forms. You can either have it in what's called a Fischer projection, organic review. Okay. There is a sign-in sheet. Let me just move this out of the way. Sorry. I wasn't sure how many people were going to come today. So in your Fischer projection, just some general things that can help you out. Anytime you see a cross, that refers to a chiral carbon. So he might show you a Fischer projection and ask you something like, how many isomers could you make from this sugar? How would we figure that out?
2 raised to the 4th power.
Right. So our number of isomers is 2 raised to the n being, number of isomers. So n being the number of chiral carbons. So like Amber said, 2 to the 4 would be how you'd figure out that. You can also see
She's coming back.
oh boy, I need more chairs already. Sorry, wasn't sure how many people were coming. Monosaccharides can also be shown in a ring structure, and essentially these can flow back and forth. So rings can open and close really readily. Does anybody know which one of these would be considered more stable? Which one of these forms?
Isn't that cyclic acetal?
Exactly, yes. So let's kind of pull back a little bit. So you've talked about functional groups called hemiacetals and acetals, okay? Hemiacetals are when you have a COC, so an ether bond, and a OH bonded to the same carbon. So we can see that here. So we have our COC and we have our COC. So this is a hemiacetal. Another functional group is acetal. So instead of your OH group, you have two ether groups bonded to the same carbon. Now, one point that can get a little bit confusing, but because you're going into your final, if you are just comparing hemiacetal and acetal, acetal is considered the more stable functional group. When we are looking at carbohydrates, specifically comparing the Fischer projection or the open to the cyclical hemiacetal, this is the more stable form. Okay, so those are two separate things. If you're just comparing these two, this one's more stable. When you're comparing these two, hemiacetal is more stable. Okay, so be careful when you have questions that's asking about stability. Make sure you know whether you're talking about monosaccharides or if you're comparing these two. Any questions so far? Okay. So in terms of classifying, it doesn't seem like he's really concerned with you memorizing sugar structures at this point. It's more of being able to classify them. So monosaccharides can be classified in two different ways. One is based off their functional group. And two is based off of their number of carbons. So the functional group, we're really referring to this piece up here. What functional group do I have there?
Aldose.
Right, so it's an aldehyde group, so because we're talking about a sugar, that's referred to as an aldose. So you can either have an aldose or a ketose. Okay, a ketose, just for reference, would look something like that. Okay, so instead of the carbonyl group being on the end, we have it in between two different carbons. So that's based off functional group. The number of carbons, again, 1, 2, 3, 4, 5, 6. The prefix for 6 is hex, so this would be a hexose. So this is an aldohexose, okay? What's the smallest number of carbons in a monosaccharide possible? 3. So a triose is your smallest one. What would the name be for, how would we classify this one? Wait, no. It is a keto.
Keto butase?
So we're not going to use the prefixes for naming. Tetros. Yep. So don't get those confused. I know that you've gotten meth, eth, prop, and bute kind of drilled into your brains. So 4 carbons, tetros, and it's a ketone group. So ketotetros. Make sense? Okay. He wants you to know that these are stereoisomers. So if I had So again, these are stereoisomers of each other. If we were to count up the carbons, hydrogens, and oxygens, they'd be identical. But we see that there's one difference here. So this OH group has flipped. There is a specific, you're gonna need to bring your own chair, sorry. Sorry, where was I? So when you have stereoisomers, where there's only one carbon that's different, okay, there is a term for that. Epimer. I know he's coming back, but we can scoot him that way. I got in the YouTube videos. So that is a term you should definitely know. You should also be comfortable identifying whether something is a D or an L isomer. Okay, so when you're asked to do that, you're going to focus in on this last chiral carbon. Okay, the location of your OH group is going to tell you whether it's a D or an L isomer. So whenever you have the OH on the right side, that's a D isomer. If it's on the left, that's an L isomer. So this, for example, would be D-glucose. Which isomer is more readily found in the environment? D or L? D. Is that the same as amino acids?
No.
Right, so something to keep in mind. So carbohydrates, naturally occurring D isomers, amino acids, L isomers. Covered that. Okay. So going back to ring structures. Okay, so these are some typical ring structures. I don't know if he'll really put these on the final, but just so you're comfortable actually seeing them. I would know the terminology for these two types of rings. So you have furanose and pyranose. You may be more comfortable with these after kind of reviewing chapter 25, because you see Hetero Cycles and you're kind of exposed to furan and pyrimidine. Not that they're identical, because those are aromatic, but at least the names seem more familiar. Along with epimer, you should be comfortable with knowing what an anomer is. So when you're in a cyclic ring structure like this carbon is considered your anomeric carbon. And so the reason for that is you can get two different isomers based off of where the OH group is oriented. So you guys might remember alpha and beta isomers from regular chemistry. Those are considered anomers of each other. So epimer, one carbon differs in a straight chain monosaccharide. Anomer, alpha or beta isomers in a ring structure. So you should feel comfortable with those two terms and being able to identify them. I talked about the fact that these can open and close. The term for that is mutarotation. So if we were to say go from this being alpha, because our OH is oriented in a downward position, if we were to open and close with the OH in a beta form, that would be considered mutarotation. Still good? Okay. So there is a way for us to essentially close this ring and keep it from opening. To do that, we have to acetylize it. Okay, and so remembering that acetal, that's essentially what we're doing. We're going to convert this hemiacetal to an acetal, and there's really two ways to do that. So we could add just a methyl group to our ring. So we've removed the hydrogen and we've added a methyl group. Now we have a COC and a CCOC. So we've acetylized it. Also keep in mind this occurs when we link monosaccharides together. So if we make a disaccharide, we have a COC and a COC. So we kind of get the same functionality. Both of these, this ring is now closed and we can't open it back up. So if we're talking about this process here, essentially what we've made is a glycoside or a sugar acetal. I don't know what term he used in lecture. But essentially what we've done is we've closed the ring. It can no longer go through mutarotation. And this is really important when we're talking about reducing sugars. So I'm going to do just a quick review here. So if we have an aldehyde group and we oxidize it, what do we expect to happen to our aldehyde group?
It'll become an alditol.
Careful, so you're actually thinking of reducing, right? Because an OL would be an OH, right? So we're going to get to that. Yeah, Kelsey. Carboxylic acid. So if you think way back, aldehydes can be oxidized. Hi, you're going to have to bring your own chair. Sorry, we're running out of chairs.
Can I just hang in the back?
Of course, if you want to. Yeah. Is that your backpack? Yeah. Okay.
You can just. No, you're gonna try and squeeze through
I
that.
need napkins.
Oh, okay.
Coffee's dripping. I'm sorry.
So the fact that we can oxidize this, okay, means that something else that we're reacting it with is being reduced, okay? So if a sugar can be oxidized, it's referred to as a reducing sugar. I know that seems kind of backwards, but it's the fact that it's reducing something else, okay? So as long as this aldehyde functional group is here, we can oxidize it, and it will reduce something else. We have a reducing sugar. Now, the problem comes when you acetylize it. So we know that this ring can no longer open. Because it can't open, we can't oxidize it. So by acetylizing a monosaccharide, we basically remove its reducing sugar functionality, okay? So if we take glucose, which is a reducing sugar, and we acetylize it, it's no longer a reducing sugar, okay? So that's really the main function of acetylizing. You're basically taking away that functionality of it being a reducing sugar. I'm going to move on to reactions. Is there any questions about acetylization? Okay. You here for organic or? Oh, okay, sorry. Okay, so this is what I just had on the board, but I just wanted to take a moment because we did bring up the alditols. So essentially, we can oxidize our sugar, our monosaccharide, or we can reduce it. So again, this is really going back to the basic concept of, oxidation and reduction. So you should definitely know that if you reduce a sugar, you're going to end up with an alcohol, okay? And Amber already used the term alditol, OL referring to the OH. So I believe he talked about, some specific types of alditols, so like xylitol, sugar replacements. So I don't know if he necessarily quizzed you on those, but I would probably know at least one version of an alditol that's used in real life. You should probably know both of these processes, because this is one of your reactions on page 2, reduction of monosaccharides. Okay. And since we're here, let's talk quickly about Feynling's and Tollans test. I don't know if he really quizzed you on these. They've come up, hi whiskey. They've come up in other chapters as well, but essentially, these two tests identify whether there's a reducing sugar. So the reagents that are used are going to oxidize or attempt to oxidize the monosaccharide. If a reaction takes place, that means there is a reducing sugar present. I would know that the Fehling's test uses a copper reagent. Tollans uses a silver reagent. Sorry, yeah.
It gets stuck in that
It does. Okay.
storm window.
Okay.
The big one will not, but the little glass thing
Got it.
does.
So again, I think it's more important for you to know the reason or the purpose of those reactions. So they identify whether there is a reducing sugar present. Okay. We're going to move on to oxidative cleavage. Okay, so oxidative cleavage, I don't think you necessarily need to know the reagent. I think he gave it to you in a question, so I wouldn't worry too much about memorizing it, but it might help you identify which reaction he's talking about. So essentially, this reaction is used to figure out the specific structure of a monosaccharide, and it does that by reviewing the ratios of its final products. So we're going to basically cut up, I'll use a different color, cut up this monosaccharide, and each piece is going to be oxidized differently. So for example, our aldehyde group is going to be oxidized to CO2. Our middle carbons are going to be not H, sorry. Okay. So our aldehyde or our ketone, it wouldn't necessarily matter in this case, they're going to be fully oxidized into carbon dioxide. Our middle carbons are going to be oxidized into carboxylic acids. And then our outer, our CH2OHs, the non-chiral alcohol pieces, are going to be oxidized into aldehydes, okay? So by looking at the ratio of these products, so essentially we're going to have 1 carbon dioxide for every 4 carboxylic acids for every 1 aldehyde. We can identify the fact that because we have that ratio, we know that this is the structure we'd be looking at. If we had different ratios, we would have a different structure. So I would focus more on the purpose, which is identifying the structure, but that's how they identify the structure. Does that make sense? I'm pretty sure there was a quiz question on that. Okay. The next two, I don't know for sure if there was an actual question on the process. I think it was more a question on something involved. So So carbonyl condensation with amine derivatives. Essentially what you have here, and I'm gonna kind of do a shortened group just for simplicity. So essentially we react this to create what's called a hydrazone. I don't think you need to know the structure, but just so you have something in your head. So this is what we refer to as a hydrazone, okay? If we continue with another round of this reaction, we have this same, I'll just put it here. We're gonna have the same structure, but we're gonna again add it here as well. This is referred to as an osazone, okay? So when you have multiple of these amine groups added, you end up with an osazone. I believe what he was focusing on is the purpose of osazones. Now, essentially, osazones are used more readily than sugars to identify melting point. So sugars tend to make what I think he referred to as like syrups, okay? So it's really difficult to figure out a precise melting point. But if we convert it into an osazone, osazones have a very sharp melting point. So it's much easier to identify where their melting point is. So again, I think less of a focus on the actual process or the structure, more on what is an osazone, why would you bother using it? The last one mentioned in Dr. Cosper's notes, I don't know if there was really a question on it, but basically it was referring to cyclic acetals. So essentially, and I'm not the best with these. I would focus less on the structure. You don't need to know the structure. So essentially, we can get a bond here. So we've now created an acetal in this cyclic compound. I think the main purpose here is that when you are adding the cyclic acetal, it's usually used as a protecting group. Okay, so more of the purpose of it, less on the actual reaction. There were two other reactions that were discussed in Dr. Fred's notes, not necessarily in Dr. Cosper's notes, and it had to do with chain shortening and chain lengthening. So this is what's referred to as chain shortening. And in this process, we're going to remove a carbon group, one single carbon group. So what we have here is a process called oxidative decarboxylation. So what's essentially going to happen, and again I'll use a shortened version of monosaccharide. So we're going to oxidize it, right? That's the first step, oxidation. We know that in oxidation, this aldehyde group is going to be converted into a carboxylic acid. Okay, oxidation and then decarboxylation. So we're going to remove that carboxyl group that we just created. So this is going to come off as CO2, and then we're going to be one carbon shorter. Again, I believe, the quiz question, not saying that that's the only thing you need to know, but I believe he was explaining this reaction and he wanted you to know the name of it, the rough reaction. but I think you should know it both ways. You should at least know that the rough reaction is involved in chain shortening. I would also recommend knowing oxidative decarboxylation. His notes also mentioned chain lengthening. I didn't see, a specific name, not like the rough reaction. I don't know if this was something you were actually quizzed on, but just in case. So essentially, we're going to react a sugar with hydrocyanide, and we're going to create a cyanohydrin. Again, I don't think structures are important here. We're going to reduce that cyanohydrin into an amine. We're going to remove the nitrogen as ammonia, and we're going to be left with a sugar that's 1 carbon longer. Again, I don't think he quizzed you on this. You may not need to know this. He may not ask you, but at the very least, I would know starting products and these intermediates. Any questions on reactions or anything that might have been in Dr. Fred's notes that I'd missed? Anything from the quiz so
Did you
far?
go over, like, chitin?
Yeah. Because we still have disaccharides and polysaccharides. So chitin is the one polysaccharide that isn't really discussed. Is it 2 T's or 1 T? One, okay. So I think the reason that it's not really discussed, the ones that you focus, or Dr. Cosper focuses on, are the polymers of glucose, and they're more readily found, obviously, in mammals and plants. Chitin is really found in insects, so that's their carbohydrate source. That's kind of what's responsible for their exoskeleton. I would know the monomer, and I know that I don't have it memorized, but I know he asked you about it.
The N-acetyl glycosamine?
Yep.
I don't know how, I just remembered that.
Is it glycosamine?
Yeah.
I don't have a fancy way of remembering that, obviously, because I first forgot it. That's just straight memorization. This is the only polymer that you have to memorize the monomer of, because, again, remember, all of your polysaccharides that are in Dr. Cosper's notes are just polymers of glucose, so that's really easy to remember. I know that he asked some questions about, a practical knowledge, like he used like an FDA person going to a peanut butter factory. But basically what he wants you to know there is if you find chitin in something, it's because there were insect body parts in it. Okay, so you should relate those two together. I'm trying to think of other questions that he had, but I think it was really what's the monomer, what is it found in, and what does it mean if you find it in food? Is there a question that I missed?
He said, like, there's an acid, like for the peanut butter thing, that breaks down insect hairs and body, like insect body parts, but
Right.
that doesn't make sense why there'd be some left over then.
So it's breaking down the hair. So basically what he's saying is it's breaking down the hair, but the chitin is still there. So you're measuring for chitin levels, which are going to be readily available because you're breaking down the hair and the body parts. So it's not saying that it's breaking down chitin, it's breaking down what the chitin is in.
Okay.
So that's a good question. Anything else on chitin? Okay. So your one disaccharide that he wants you to know, disaccharide meaning 2 sugars, is sucrose. You should know what sucrose is made out of. So sucrose is glucose plus fructose. And they're linked by what type of bond?
Acetal bridge.
It is an acetal bond. I don't know if you use the other term for it, glycosidic.
Yeah.
Okay, so it's a glycosidic bond, and the functional group of that glycosidic bond is an acetal, which we kind of already talked about when I was talking about acetylation. So I would like to point out that both glucose and fructose are reducing sugars, okay? However, when they're in sucrose, sucrose is not a reducing sugar, and I'll show you why. Okay, so I talked to you about the anomeric carbon. Okay, so that's the carbon where we have alpha and beta forms, and if we acetylize that carbon, we can't open the ring anymore. Okay, it becomes closed. So I know that, you know, I sometimes kind of do a shorthand of glycosidic bonds like this. Here we see one anomeric carbon locked, but this one is not locked, right? It's not acetylized yet. However, when we look at sucrose, both of the anomeric carbons are in the glycosidic bond, okay? So because of this structure, both of these rings are closed. Neither of these rings can open up, meaning that this is not a reducing sugar. Even though glucose and fructose alone are reducing sugars, sucrose effectively closes both of the rings, so sucrose is not a reducing sugar. And kind of an aside note, if you get questions on reducing sugar, if it's a monosaccharide that he's talking about, you can assume it's a reducing sugar. If you're talking about sucrose or any of your polysaccharides, you can assume that it's not a reducing sugar. Okay? The only way to break that glycosidic bond is to react it with an acid, and you end up with 4 different monosaccharides being formed. Did he ask you about invert sugars on your quiz?
Yeah.
Okay. The fact that, so you react it with an acid, and you get 4 monosaccharides. This process is referred to as an invert sugar. Okay? So sucrose is considered an invert sugar. The last piece is really your other polysaccharides. So we already talked about chitin. The next 3 you should really know, and again, I'm not sure what he actually quizzed you on, but I think it's always a good thing to know where they're found, the function, and any of the bonding that occurs. So I'm just going to make like a chart, basically. I think that worked in the past. Does everybody have this? Or
You could.
okay.
I'm gonna.
So what are the 4 polysaccharides that you guys discussed other than chitin?
Cellulose,
Okay.
amylose, amylopectin, and glycogen.
Good. Amylose and amylopectin together are typically referred to as starch. So if you remember him talking about starch, he was really referring to both of those. So again, where are they found? What's their main function? Bonding. And is there branching? Okay. Where is cellulose found? Plants or animals? Plants. What about amylose and amylopectin?
Animals.
Plants.
Plants, actually. We eat starch, but we don't actually use it in our systems. We eat it and then break it down for energy. So glycogen is actually the only one that's found in animals. Their main function, really what we're referring to there, is whether they're used for structure or for energy. Only one of these is used for structure, and I already mentioned it earlier, cellulose. Cellulose is what gives plants rigidity. So the rest of these are used for energy. In terms of bonding, really what we're talking about is the glycosidic bonds. And it's, there's really only one difference, and it has to do with whether something's alpha or beta. So when we're talking about bonding, there's really two different components. Is it an alpha or a beta bond? And what carbons are linked together. So for all of these, carbons 1 and 4 are linked. So the only difference is it an alpha or a beta bond? Which one of these is beta? Cellulose. You're noticing, you might be noticing a pattern here. Cellulose is kind of the exception. So this is important because this is the why for why we can't break down cellulose. So our enzymes are specifically made to break down alpha 1,4 bonds. That is their job. If they come across a beta 1,4 bond, even though the same carbons are bonded, our enzymes can't break it down. So cellulose does not provide any energy for us. I'm not going to talk about the branching bonds, just whether something has branching. So 2 of these have branching, 2 of these don't. Does anybody remember which one of these have branches?
Amylopectin and glycogen.
Good. Any questions? Okay.
Do we need to know the 1,6?
I don't think he really quizzed you on that. It doesn't seem like that's really a big, if you take like biochemistry, you'll come across these again, but I don't think you necessarily would need to know them. If you do, the ones that have branching, it's alpha 1,6. But again, I don't think that'll be a focus necessarily. But that's chapter 24, unless I missed something that you guys remember from lecture. Yes?
It's not from lecture, but it's because I came in late. So what, again, is the definition of reducing sugar?
Yeah, so a reducing sugar is just a sugar that can be oxidized.
Sugar that can be oxidized.
And you can really assume that any monosaccharide can be a reducing sugar. It typically is only not a reducing sugar if it's been acetylized. I know somebody at the beginning mentioned chapter 25. I know we discussed it pretty heavily yesterday. If there's a specific concept or something that you, like a reaction or something, I'd be happy to go over it in more detail. Or if there's another chapter that you guys might want to talk about. Yes? No, we haven't. Yeah. Chapter 20, right? Yeah.
Well, thank you.
Okay. Okay, so again, remembering that chapter 20 really builds after chapter 19, so I would definitely recommend, I don't know what the question breakdown is, but chances are you need information from chapter 19 to answer questions in chapter 20. So again, this is really the semester of functional groups, so I would highly recommend reviewing those before the exam. So since we're here, anybody know this functional group?
Acyl halide,
Good?
anhydride, ester, amide, nitro.
Okay, alright. In terms of reactivity, you should definitely know that these are the most reactive. So acyl halide, most reactive, and then as we work our way down, we become less reactive. This really depends on the leaving group, which makes sense. We know that halogens are typically good leaving groups, so it makes sense that something that has an acyl halide is going to be fairly reactive. And then the next piece isn't as neat to say, but basically the effect of leaving. So how does leaving affect the state of this carbon? Is it going to, is there going to be an opportunity for residence? Is it going to be less stable? So the less stable the carbon is after it leaves, the less reactive it's going to be. Okay, so just some thoughts on that. Yes?
Is nitrile included in that?
No.
Okay. All right.
Nitrile is kind of on its own in that case.
Okay.
Okay. It goes into some more specifics, but again, I don't think that's necessarily important. Okay, so all of these have a carbonyl group. Knowing that, where would we expect them to be in carbon NMR? Downfield or upfield? Downfield, because they're de-shielded. How do you know that they're de-shielded? Uh-oh, guys.
If it has to do with the carbonyl group, is it because of the double bond L?
So there are two different things. So having an electronegative atom, so the oxygen, yes, but also the pi bonds. Pi bonds tend to pull on the electrons as well, de-shielding the carbon and the surrounding hydrogens. So it's kind of a twofer, okay? So electronegative atom, pi bonds, de-shielded. All of these are going to be de-shielded. Going into nitrile a little bit more. Again, kind of an overarching theme you should definitely be comfortable with, orbital hybridization. What is the orbital hybridization of this carbon?
SP.
SP. How do we know it's SP?
Because it's triple bond, or it's a triple bond.
Okay, that's one way of thinking of it. So people that have come to a lot of these sessions know that I focus on attachments. So we have two attachments here. Okay, we have an R and an N. So each attachment corresponds to an orbital. So 1, 2, SP. If we had something like this, we have 4 different attachments. So S, P, 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 1, 2, 3, 4. This is SP3. So that's my method of using it. Again, it's pretty much in every video because orbital hybridization comes up a lot. So our carbon is SP. What about our nitrogen?
That's SP2.
It's actually SP as well, okay? And that has to do with this electron pair that's here. So even though it's not written in our condensed form, you need to know that there's an electron here, electrons there, and those electrons are going to count as an attachment. So in this case, our carbon and our nitrogen are both SP. What would we expect the geometry of this molecule to be? linear. So SPU should link with linear. Okay. What about SP3? What shape would you expect there?
Trigonal.
Tetrahedral. Okay, tetra, right? Tetra 4. Trigonal pyramidal would be something like, well, actually, be careful. Trigonal pyramidal is just another type. Trigonal planar would be something like NO2. Don't think you need to know that. So specifically talking about nitriles, if we were to run this in the NMR, would we expect this to be downfield or upfield? Downfield for the same reasoning. We've got pi bonds and we have a nitrogen, so that's going to de-shield the carbon and the corresponding hydrogen. Any question on nitriles? Did he ask you questions on lithium aluminum hydride and dibol?
Yes.
He did. Okay. Did he ask you to, like, did he mention them in a question and you had to know what they did, or did he want you to, like, pick out, like, dibol?
Yeah, to know.
Like the product.
The product.
Product. Okay, great. So there's a nice chart in Dr. Cosper's notes that I would recommend using. You don't need to know the structure of dibol. Essentially, these are both reducing agents. What you need to know is whether one is strong or moderate, not as strong. So lithium aluminum hydride is considered a strong reducing agent. Dibol is considered more mild. So when we use lithium aluminum, when we use this one, we're going to expect our reactant to be fully oxidized, okay? So if we, fully reduced. Sorry about that, these are reducing agents. What functional group is this?
Ester.
Good. So again, we're reducing. What are you thinking the most reduced form might be?
Alcohol.
Yeah, so easy to see in Dr. Cosper's notes. But remember that we're going to remove these carbon-oxygen bonds, or most of them, and so we're going to be left with just one carbon-oxygen bond. So we go from 1, 2, 3, 4 to just 1. So this would be considered fully reduced. On the other hand, we would end up with this. What's this functional group? An aldehyde. So ester, fully reduced with a strong reducing agent, is an alcohol. With a mild reducing agent, aldehyde. Okay? If we're using an amide or a nitrile, instead of an alcohol, we're going to be creating an amine. And really that's just because instead of this oxygen being left over, our nitrogen is going to be left over here, okay? So because we have a nitrogen present, that's what's going to be present in our final product. So amide or nitrile with a strong reducing agent, we're going to get an amine. With these, with a mild reducing agent, we're still going to end up with an aldehyde. Okay? Just knowing this information, again, thinking back to the quiz, would you be able to answer the questions that he was asking? Does this all make sense? Okay. I really think that there are, out of the 4 on the back, there are 3 that are more important. Grignard. And then Hofmann. So with trans-esterification, essentially we have an ester and an alcohol. And all we're doing is switching the alkyl groups, okay? So the alkyl group in an ester is going to switch places with an alcohol. So that's all that happens. Trans-esterification. Switch alkyl groups. Okay, nothing too fancy there. This one I think is pretty important, especially considering nothing is bolded in Dr. Cosper's notes. I do think that this one is important. You should remember Grignard reagents from either previous chapters or last semester. I can't remember if you spoke about them. But essentially, we're going to take an ester and a Grignard reagent. Now, I don't know if you remember Grignard reagents basically use organometals, so like magnesium. Essentially what we're doing here is we're reducing. So we're using a Grignard reagent, we're reducing an ester, and what we're going to make is a tertiary alcohol. Any questions on these two? Okay. Hofmann rearrangement. What is this functional group? Amide, right. So nitrogen bonded to a carbonyl group is amide. So Hofmann rearrangement. We're going to pull out this carbonyl group. It's going to leave as CO2. And then we're just going to bond the alkyl group with the nitrogen group. So essentially, we're going from an amide to an amine with carbon dioxide. That's really chapter 20. Anything that I might have missed thinking back to your quiz or midterm? This was on your midterm, right? Yeah. Okay. How are we doing on time?
Yeah, like an hour.
Okay. Somebody else want to throw a chapter out there?
Can we just go over some naming?
Sure. Okay. Why don't we first think about what you do need to know in terms of naming. So, alcohols, diols, aldehyde, ketone, Did you actually name esters?
Yeah.
Yeah.
You did? Okay. What about ethers? No. Okay.
Diethyl, like that.
There's another one that I'm missing. Anhydrides.
Yeah.
That was like a bonus question. He was like, you can do it.
What am I missing?
Amides.
Did you actually name them?
Yeah.
Oh, okay.
I named a lot.
We had to do a matching one that he did everything.
Right.
It's like,
Did he talk about benzene derivatives?
Yeah.
Okay. Am I missing anything?
can you do an amine too?
we'll talk briefly about hetero cycles. I don't think you need to know how to actually name them. I think you need to be able to pick some of them out. Okay. I think those are really the main ones. Okay, thank you. So one thing to keep in mind, and it was brought up yesterday, knowing which one of these holds the highest priority. So in general, you're going to give the most oxidized functional group highest priority when naming. So really that means if you have an alcohol, alkene, and a carboxylic acid all in the same molecule, what do you give highest priority to? In that case, in pretty much all of these, carboxylic acid is your highest priority because it's the most oxidized carbon you're going to see. So regardless of what's present, if you have a carboxylic acid with something else, you got to give that carboxylic acid first priority. So let's see here. Naming alcohols. So again, the process, you want to continue using the same process from last semester. So you first want to identify the longest carbon chain. So in this first one, what's the longest carbon chain?
Propanol.
Okay, yes. So taking a step back. So 3 carbons. The prefix for 3 carbons is prop. Or propan. And we add the OL for alcohol. Okay? Is there anything missing from that name? The number. So what would the number be for this one?
2.
2 propanol. How does this second one differ from the first one?
2 hydroxyl groups.
Good. So what would be the general category of this? Yes, it's an alcohol, but it's a special type of alcohol. It's a diol. So how would we name this?
Butane, butadiol.
Good. So that's, yep, butane, because it's all single carbons and the longest chain is 4 of them. And we have to add diol to reference the fact that there's 2 hydroxyl groups. What are we missing? Which would be 1,4. Make sense? So for these two, how do we differentiate between aldehydes and ketones?
Aldehydes are on the end.
Good. Another way of remembering that, if you're having a hard time, aldehyde has an H in it, and because it's on the end, that carbon is always going to be bonded to a hydrogen. Okay? So here our longest carbon chain is 5 carbons. What's the prefix for 5 carbons?
Pent.
And it's all single bonds, so pentan. What suffix do we use for aldehydes? Al. What do we use for ketones? Exactly. Are we missing anything in this name?
No,
Why wouldn't we use a number in this case, Amber?
because aldehydes are all terminal.
Exactly. So it's assumed, because you're saying it's an aldehyde, that it's going to be on the first carbon. Using the number is redundant, and I know he's marked you off wrong for using redundant numbers, so be careful of that. On the other hand, if we're talking about ketones, how would we name this ketone?
2 pentanone, 2, 3, 4, 5, 6 hexanone.
There we go, yep. So why 2-hexanone and not 5-hexanone?
Because you name from the, I know the reason, I just can't spell words.
Closest to the carboxyl group.
Yeah. Or
Right, so you want to give this
The lowest
carbonyl
number.
group the lowest number,
Lowest
exactly,
number,
yes.
yeah.
So it doesn't matter whether you're talking about left to right, you don't have to specifically start on one end or the other. You want to give the carbonyl group the lowest number. So numbering it from this way gives it a 2, which is obviously lower than 5. Excellent. What if we had that? How do we name that?
2. Again. 2 pentanone.
That's acetone.
That's the common name. What would the IUPAC name be?
It's 2-propanone.
Yeah, so be careful, use the different
I
P's.
said
So it was propanone. Did you say 2-propanone? Would we need the 2 here? If it's a ketone and there's only 3 carbons, there's only one place for the carbonyl group, right?
okay.
So that's another redundant number.
So you
So it
think
would just
you
be
mark this out?
propanone.
Okay.
Those are the ones to be careful of, right? He likes to show smaller molecules anyways, so chances of that happening are actually pretty good. So like aldehydes, carboxylic acids are always on the outside. So does that mean that we need to number them when we're naming? No, because they're always terminal, you can assume that they're going to be on the first carbon. You should know how to do IUPAC naming definitely, but you should also recognize that this is a very specific molecule that he wanted you to know the common name for.
Acetic acid.
Acetic acid. This is probably one of the few common names that you really need to know. To help you out, acete is the common prefix for 2. So acete and F are synonyms of each other. Also notice that the ending is slightly different. In the common name, you just use IC and not. How would we name this with IUPAC naming?
Ethanoic acid. Well, we have to know methanoic acid or formic acid, or is it mainly acetic acid we'll focus on?
From my memory and what I've seen this semester, acetic acid is really the only common name you need to know. That just has to do with how much it's used in industry. I think he just wants you to be able to recognize it because nobody in industry would ever call that ethanoic acid. They would just call it acetic acid. But notice the naming convention is slightly different. If you put acetoic acid, I think he would still give it to you. But just be careful there. They don't use an O in common naming. Again, if we end up with something like this, just like with diols, this is now a dioic acid. I think this might have actually been one exactly on one of your quizzes. So how would we name this?
Propandioic acid.
Exactly. So 3 carbons is prop, all single bonds, AN. Dioic to reference the 2 groups. And again, with this you wouldn't have to worry about. So remember with alcohol groups, the alcohols can be anywhere, so you would have to number. With dioic acid, because we can expect them to always be on the ends, you do not need to put numbers here. Okay. Esters are one of the more complicated ones, I'm not going to lie. I'm going to go into a little bit of detail as to how esters are formed, which is going to sound like a tangent, but it does help with the naming process. Okay, so bear with me for a little bit. Does anybody remember how esters are formed? What are the 2 reactants in esterification?
Alcohol
And?
Carboxylic.
Right. We know, you should remember, these are carboxylic acid derivatives. So carboxylic acid and alcohol. I'm just going to do a simple alcohol. Okay. So I want us to first name our carboxylic acid and our alcohol. So how would we name our carboxylic acid here?
propanoic acid.
and our alcohol.
Methanol.
Okay, and I'm actually going to use two different colors just to make it a little bit more clear. Okay, so esterification is a dehydration reaction. So we're going to heat this up and we're going to remove water, okay? So essentially what we're going to do is we're going to remove this hydrogen and remove this OH group, okay? So that's going to fly off. And then we're going to combine these two molecules together. So okay. Does everybody see how we did that from one to the other? Okay. So the reason that I'm telling you this, an ester name has two different parts. The first part comes from the alcohol. I'm going to shorten that because it doesn't need to be that long. And the second part comes from the carboxylic acid. Okay? So the alcohol part. So we've removed the OH group, and essentially all we have here is an alkyl group, right? A small hydrocarbon unit. Okay, so if we think back to when we had alkyl groups on just an alkane, if this was a substituent, how would you name that?
Methyl.
Methyl. One carbon coming off of the main chain, methyl. Now bear with me because this one, the next part gets a little annoying. So we have a carboxylic acid. When we remove the hydrogen, we're actually going to leave a kind of negative charge on our oxygen. So essentially what we're creating is a carboxylic acid salt. Remember, a salt just refers to something that has ionic charges, okay? So we're going to take our carboxylic acid name and change it to a carboxylic acid salt. And really how we do that, we drop the ic acid and we add 8. So it goes from propanoic acid to propanoate. So this ester is methyl propanoate. Does it help to go through the beginning process? So again, remembering, he will most likely not show you this. This is what you have. So you have to figure out what your starting products were to really name it. So again, I would make sure that you keep your carboxylic acid group to one side. So you're going to always want to cut it to make sure that it's on that side. So again, we want to make sure that our carbonyl group and the oxygen are on the same side, regardless of which way it's drawn. Do you want to do another example of ester? Or do you want to move on to the next? Move on? Okay. Bless you.
Bless you.
Okay. Anhydrides are actually probably simpler than one of the more simple ones, I guess. Basically, he would have to tell you what acid was used to make that anhydride. So for example, I believe in lab you use something called maleic acid, and you converted it to an anhydride. That anhydride's name was maleic anhydride. So that pattern goes for every anhydride. As long as you know the acid, bless you, that anhydride is just going to be the acid name with anhydride replacing acid. So I believe if he did ask you a question, he did ask you a question on this, right, on one of your quizzes? I think so, yeah. He has to give you the acid name, okay? So I wouldn't overthink this one too much. But does that make sense? Okay. Why don't I remember us going over naming amides? I know we went over naming amines.
I don't know if we did.
I don't think.
He drew one, we had to know what it looked like.
Yeah.
Okay, yes. So you should know how to identify all of these, but you don't necessarily need to know how to name amides. I was a little surprised by that one. We'll go over amines, but you should be able to identify any of these functional groups plus more. These are just the ones you should know how to name.
So amide is an NH2 attached to a carboxyl
I would be careful with the
Or carbon.
NH2. Just nitrogen bonded to a carbonyl group.
carbon, yeah.
Okay, because it could be NH2 or it could be bonded to something else.
Okay.
Okay, but just for simplicity, this is your amide functional group. Okay, benzene derivatives. Okay, so by now you should all be really comfortable recognizing benzene, right? Why is it drawn with a circle in the middle?
It's 3 double bonds.
3 alternating double bonds, right? And because we have alternating double bonds, essentially the double bonds can rotate, meaning that the electrons can move, so that's why they draw it as a circle. So you should be able to recognize all of these. I know there are more, I think in chapter 15. Not saying that you won't also be asked about those, but I think these are a good place to start. So the 3 on top are sometimes the harder ones to remember. Does anybody remember these common names?
Phenol,
Good?
toluene,
Good. Phenol, toluene, and
and
aniline. Okay, definitely know those names. If you said methylbenzene, he might give it to you, but you might as well just memorize toluene. What about these guys?
Benzaldehyde,
Good?
benzoic acid. Well,
That one, I don't know if you're gonna, but benzyl alcohol, you might have it come up. So these are your benzene derivatives you should know. Also keep in mind, he could add a substituent. How would we name this?
two,
3-ethylphenol. Okay, so phenol being the base, and again, OH group is higher higher priority. So 1, 2, 3, 3-ethylphenol. So again, you should be able to add any of these substituents to these benzene derivatives and still name them.
for the benzyl alcohol, that was if you reduce it with MnO2, you get a ketone.
Be careful. I don't know what chapter I know what you're referring to, I just don't know what chapter it's in. But you wouldn't be able to reduce this and get a ketone.
So what was that?
I'm trying to think.
I think it's 23.
Oh, it's 22.
almost there.
Oh, it's
It
oxidized.
was one of those.
Okay, that makes more sense. And it was that reagent that you mentioned, the
Yeah.
manganese oxide? Okay.
It's MnO2.
Yep. Okay, so that would be probably where you would need to know it. I will say this one was not mentioned in chapter 15, but it does come up in later chapters. Okay. Ready to move on? Did he give you a means to name that had more than one carbon group on the nitrogen? Okay, we're not. Okay, so remember that nitrogen can make 3 bonds. So in terms of classifying, you should be able to classify primary, secondary, and tertiary amines. In terms of naming, let's just focus on one carbon attachment. So if we had something like this, okay? We're going to take our alkane name and add amine to the end. So if we were just naming the alkane here, what would the alkane name be?
Pro.
Right. So we're going to drop the E and add amine, propanamine. So methanamine, ethanamine, propanamine, you kind of get the idea here. What if we had something like that? We have 2 amine groups.
1 for butanamine.
Butanamine, there we go. So 1, 4, butan,
Diamine.
there we go. You're noticing a pattern here with the multiple functional groups. Just make sure that you get that di in there. And again, remembering aniline kind of falls under this one that you need to remember. Okay. Let's do acyl halides first, because it's a little bit easier. Okay, so remember acyl halides are just a carbonyl group with a halogen attached. Really, we're just going to replace halide with the specific halogen name. So if this was chlorine, it'd be acyl chloride. So what would it be if it was iodine?
Acyl iodide.
Yeah, exactly. Not too bad. In terms of heterocycles, let's talk about general ones, like just general naming, and then specific names to identify. So remember that heterocycles either have oxygen, nitrogen, or sulfur as one of the members of a cyclic system. Each of these corresponds to a specific prefix. So if you have oxygen in something like this, how would we name that? Cyclo what? Butane, right. So we're adding oxa. And noticing that I've always done it like this, but then I've seen him put the E in there. I've seen it as this as well, but I would follow his naming procedures. What about nitrogen? What's the prefix corresponding with nitrogen?
Aza.
Again, I've seen aza more often. It does look like they have aza, like AZE here as well, but I think those two you should use. And then what about sulfur? Exactly. Okay, so in terms of naming, you should be pretty comfortable with any of these cyclic or cycloalkanes. So how would we name this one?
Aza cyclopropane.
Exactly. And then
6-dicyclohexane.
exactly. Okay. So you should be able to use any of these with any size ring and be pretty comfortable. Some other ones, kind of like your benzyl aldehydes. So you have furan, pyrrole, thiophene. Okay. Would also recommend pyrimidine or pyridine. Pyridine. For quinoline and isoquinoline, I don't think he really asked you much on your quiz about these, but just knowing that quinoline, both of them are a pyridine linked with a benzene, that's really the more important thing to know. I don't think he's going to have you identify the structure, but that is important.
About indoles. We'll talk about
I don't think you need to know the structure of indole. I think you should know their purpose. I don't think structure is really going to be emphasized.
Like he drew I think he drew an indole and we had a name
Oh,
on our quiz.
I feel that.
Really?
I think it asked a question with it. He just had so it'd be good to know it.
Okay. But he asked you to name it?
Yeah.
Okay, I don't know how to name indoles. So.
Oh no, like say it was
Oh,
an
I was okay.
indole. Yeah.
Got me all nervous, guys.
So quinoline and isoquinoline have just the N or nitrogen. Indole is NH.
Yes, yeah. So,
Or not.
with a
Okay.
benzene.
So this is another.
Basically, okay, so if I draw benzene here.
Oh, I see it now.
Okay, so benzene and pyridine, this is quinoline. Here we have benzene and pyrrole,
Pyro, okay.
and that's going to give you indole.
Remember this pyro.
Got me all nervous about naming indole. Okay. It has been a term that's thrown out here, and it has been thrown out here before, azobenzene. So pyridine is an example of an azobenzene. But remember, it's more than just pyridine. There are a variety of azobenzenes. This is just one example of them.
Azobenzene is just a.
It's kind of just
Benzene.
playing off of the fact, so aza, nitrogen in a benzene
and
ring,
benzene ring.
right? So there's a lot of variety of them. You can have more than one, but pyridine is a common example of an azobenzene.
Is that those are two benzene rings?
This is a benzene and this is a pyridine because we have a nitrogen. That was a lot of naming. How do you all feel?
Hmm. Okay. No one wants to say nothing.
Is there supposed to be a double bond in the?
Oh, sorry. put an extra
I
one
think
in.
in the other one too. Unless I
Did I draw it incorrectly?
There's only 2 bonds.
Any other questions on these or any functional groups that you're having trouble with? Another chapter to go over? Yeah.
I just had a question about 26. It was, I don't know if I'm just stupid, but it's saying something about amino acids being L.
Yep.
What is L?
So, when we talked about carbohydrates, I mentioned the fact that there are Dnl Isomers.
Oh, okay.
Yep, so it's the same concept. Amino acids are enantiomers, so they're going to have Dnl options. But unlike carbohydrates, amino acids are found in nature as the L isomer. So carbohydrates D isomer, amino acids L.
Is there another word for it? Just L?
Just L.
Okay.
Yep. Good question though. Yes.
Chapter 16.
Okay.
So, activators and deactivators, ortho-para, meta, like I understand where they go, where they'd be on the benzene ring.
Mm-hmm.
Like,
How to identify them?
how do I identify them? Like
Yeah.
seeing one and
This is a good one. Also, if we get cut off or, if you're also having confusion, was it last week? Last week we talked about this as well, so there is a video that might be helpful just for review purposes. Okay, so Ortho-Para Directors basically have 3 different options. We'll use the 3 different options. So for you to be an Ortho-Para Director, you either have to be an alkyl group, so just carbons and hydrogens, or you need to have an electronegative atom directly attached with free electron pairs. Okay. 3, and I'll actually do like a subset. I'll do like 2A. Because it technically falls under this, but you can be a halogen. So keep in mind a halogen is an electronegative atom. It does have free electron pairs. We'll talk about why it's sometimes easier to talk about it as a subset of number 2. So an example of this. You can have something like, okay, just an alkyl group, or you can have an OH group, okay? So again, he's probably not going to make this easy for you. You have to know whether there's free electrons there or not, okay? So knowing that oxygen makes 2 bonds and has 2 lone electron pairs, we know that it has free electrons, okay? So all of these are Ortho-Para Directors. However, in terms of activators versus deactivators, these 2 are considered activators. This one is technically a mild deactivator, but it still goes Ortho-Para. This is probably the confusing one, which is why you talk about it separately. Number 2 is considered a strong strong activator. Number 1 is considered a weak activator. Okay? But they all go Ortho-Para. Meta is anything else. Okay. So we know that it's not an alkyl group, right, because we have some oxygens present. However, the electronegative atoms are not directly attached to the ring. The carbon is what's directly attached to the ring. And the carbon doesn't have any lone electron pairs. Okay, so we don't meet the criteria for number 2. It's not just a halogen, and it's not an alkyl group. So this is going to be a strong deactivator, and it's going to go meta. Anything that goes meta is going to be a strong deactivator. Let's do some examples. Okay, so for each of these, I want you to tell me whether it's an activator or a deactivator, and then I want to tell you where it's going to direct. Okay? Activator or deactivator? Deactivator, because the carbon is what is directly attached to the ring. And there's no free electron pairs, and the carbon itself is not electronegative. So, yep.
For the halogens, it has to be directly attached as
Yep,
well.
directly attached. So deactivator, which means where is it going to direct?
Meta.
Meta. Activator or deactivator?
Deactivator.
Deactivator, because it's a halogen,
Oh, that's right, okay.
but it is going to direct where?
Ortho.
Ortho-Para. Okay? Activator or deactivator?
Deactivator.
Good. This is the hardest one, okay? People that have, I don't know if he's used it on quizzes or if he's made a point to talk to you about it. NO2, it looks like it follows criteria number 2, right? The nitrogen is electronegative, it's directly attached to the ring. The trick here is there's no free electrons. Basically you have the nitrogen typically makes 3 bonds and then has a lone electron pair. Here it has 4 bonds. So because there's no electron pairs, this is a deactivator and it directs which meta, yeah? Activator or deactivator?
Activator.
Good. What it directs?
Ortho-Para.
Ortho-Para.
Electronegative.
Now this one is different from this one. So we have our 3 bonds here, but we have our lone electron pair.
Can you draw out the NO2 like
Yeah.
that?
Like
So,
what?
Like how you just did for that one?
This one? Wait,
Yeah. Can you like draw out the NO2?
like this?
Oh, is that? Oh,
Yeah, this is what it's gonna look like. Yeah,
That's-
no, that's
Sorry.
okay. That's okay. Yeah. So, unfortunately, to know this one, you have to know how to draw the Lewis dot structure. It is a little bit of a weird one, which is why you get this going here. But yeah, so you have 1 bonded oxygen, a double bonded oxygen, and then an attachment to the benzene ring. So there's no opportunity for our lone electron pair that we have here. Nitrogen has 3 bonds. Nitrogen has 4 bonds.
Okay, alright.
And
That's the difference.
That's nitrobenzene, right? The NO2 and
Yes.
the benzene.
Yes.
So for NO2, no free electrons on the nitrogen because it is
Exactly.
alright. Attached. Directly attached. 3 electron pairs with 3 electron
Activator, deactivator.
pairs.
Deactivator. The carbon is not electronegative and it does not have a lone electron pairs. So this would be a meta director.
Halogens.
Any other questions on these? What's the time?
11:07.
Okay. 20 minutes left. A different chapter, different topic. quiz questions?
This I might be able to get.
For chapter 25 or for everything? We'd have to go through. Okay.
Thank you.
Yes. I think what might be the better thing is just looking at general, because I think if I start listing off, so, I don't know if you're gonna like this though, because it does require thinking. It's not. So think about these reactions more broadly than just, will it happen here, will it not happen here? If you're electrophilic aromatic substitution, that means you're looking for things that are electron rich. So the best thing to do is identify, is the reactant that I'm looking at electron rich or electron poor? Okay? So, attacks electron rich. So this, I think, pretty easily refers back to chapter 25. It does come up in chapter 15, and I'm sure a few other chapters. But when we think of an electron-rich ring, your first thought should be benzene. So benzene and benzene derivatives that are, actually any of your benzene derivatives are going to undergo electrophilic aromatic substitution. Depending on the derivative, so for example, if you have a deactivator being added, that just means that you're not going to have subsequent EAS reactions, but that initial one will still take place. So nucleophilic aromatic substitution, that's going to be something that's electron poor. Again, thinking back to chapter 25, we referred mainly to pyridine. Typically, and I can't say it always, but I foresee questions that are going to be phrased either one of two ways. He's going to say, benzene is an electron-rich ring. Would it undergo electrophilic aromatic substitution or nucleophilic aromatic substitution more readily? So knowing that it's electron-rich, you would assume EAS. Or he might say, pyridine undergoes NAS more readily than EAS. Why? Because it's electron poor. So I think you're going to get more questions like that. That's a really good question though. It's just, it spans multiple chapters.
Can you go over alpha, beta, unsaturated carbonyl compounds?
Anything specifically about them or just?
Just like their structure.
Okay.
They can be,
Is that chapter 18? Yeah.
yeah, they can be conjugated and non-conjugated.
Yes, they can.
What's the reaction that gives that?
There's a
Aldol
few.
condensation.
Yeah, I mean, there's the aldol condensations, but then you can also have cyclic ones, which is the Robinson annihilation. Yeah, there's a lot that goes on. Okay.
This is chapter 18.
Yes. So let's talk about what alpha beta unsaturated carbonyl compounds are. So kind of a long name. I find it easier to kind of go from the back. So carbonyl, we have a carbonyl group present, okay? Alpha beta unsaturated. Unsaturated, you should already have, linked in your mind with alkenes or alkynes. Typically, you're going to see alkenes more than alkynes. So unsaturated refers to the fact that there's a double bond. Alpha beta is in terms of location. So this refers to the carbons that are involved in the double bond. So when we're looking at our carbonyl group, any carbon that's directly attached is considered an alpha carbon. Any carbon that's attached to an alpha carbon directly is considered a beta carbon. So we have an unsaturated double bond between the alpha beta carbons in a carbonyl compound. Okay. Now, I think, Amber, I think you were referring to, oh, you can have, okay, I see. The non-conjugated also comes up when you're talking about dienes, still the same concept. So this is considered conjugated because we have alternating double and single bonds. Same with dienes. If you have double, single, double, that's a conjugated diene. Unconjugated would be something like this. Sorry for the messiness. So it still have the same numbers of carbons and hydrogens, but we see that we have two single bonds in between the carbonyl group and the carbon-carbon double bond. So this would be unconjugated or non-conjugated. This would be conjugated. Which is more stable?
Conjugated.
Why?
The alternating.
The alternating double and single, but what does the alternating double and single allow for? Resonance. Electron delocalization, meaning resonance. So if we don't have alternating double and single, electron delocalization isn't possible, so it just is more unstable. You don't have that added stability there.
With the conjugate addition to alpha beta, so I understand, you're adding some molecule, I can't think of my words, to it to get rid of the double bonds.
Mm-hmm.
Are there specific molecules that he will mention or that we need to know that they are just?
I can't say specifically. Any type of addition that you talked about last semester is possible, and that's really because really we're just talking about a carbonyl group and an alkene. So any reaction that will happen to an alkene or carbonyl group can happen to this. So for example, hydration, hydrogenation, anything like that. I wouldn't be worried about what's being added, because typically, I could foresee him drawing this structure out for you and then saying, we're going to perform a 1,4 hydrogenation, indicate what the final product would look like. So you need to know what 1,4 is referring to versus a 1,2. Okay, and you need to know where the additions are going to be taking place. So 1,4 addition means that both of these pi systems are going to be disrupted. 1,2 addition means that you would either have the addition here or here. So one of your double bonds would be retained. Okay, so if we're doing a 1,4 hydrogenation, okay, the 1, 2, 3, 4. That means the addition is going to happen here, and it's going to happen here. So essentially what we're going to end up with hydrogen, hydrogen, carbon, hydrogen added here, carbonyl group removed. What am I forgetting? And then our double bond would shift from here to here. There is room for another addition there. Typically that's going to be hydrogen. He might also make it more simple and just ask for you to point where the additions were going to be taking place. So it might just be something simple like that. I know he doesn't have you do too much drawing.
Why wouldn't both of the double bonds be gone if you added 2 additions?
So they are, this one and this one, but we've had to shift the electrons. So both of those pi systems have been disrupted, but we had to shift some of those electrons. Let's go back a little bit. If we're talking about a 1,2, he might say, technically there are 2 different places where that can happen. So a 1,2 is either going to happen here and here, or here and here. So if he were to ask you that, he might just say indicate one of the areas where a 1,2 addition can occur. Okay. Since we're already on this topic, why don't we briefly go over aldol condensation? So aldol condensation is what makes alpha beta unsaturated. Essentially, we're going to react 2 carbonyl compounds. So it could be an aldehyde or a ketone. And we're going to make something like this. This is just one example. Okay, so you can kind of see where the 2 aldehydes were originally. The second piece is just a dehydration. Okay, we're eliminating an OH and a hydrogen, and that's going to force a double bond to form here. So we have our carbonyl group, alpha carbon, beta carbon. Okay, so aldol condensation, you react 2 carbonyl compounds and then dehydrate it to form your alpha beta unsaturated. I would know that depending on the type of aldehydes or ketones that you use, you can get multiple products. What's the reaction referred to as if it creates multiple products?
Mixed aldol condensation.
Good, or crossed aldol condensation. I think you're thinking of mixed Claisen condensation, which is the same thing but with esters. So a crossed aldol condensation. So what's the, how do we prevent a crossed aldol condensation?
Having one of the aldehydes or ketones that has no alpha hydrogens.
Right, so let's talk about that a little bit. So we have one of the important pieces of this first step is we need to form enolate ions, okay? So we have to have at least one enolate ion form for the 2 aldehydes to come together. So in this case, both of these can form enolate anions. And as Amber said, it's because they have alpha hydrogens. These alpha hydrogens are the ones that are removed, and that's going to create your enol ion. So again, this could turn into So we removed one of these hydrogens, and that's going to create a negative ion. Okay, this is what's going to drive the reaction to actually take place. However, both of these can make enolate anions. So essentially what happens is a big mixture of different types of final products. So as Amber said, the best way to prevent this, instead of using something that can make an enolate ion, we need something that doesn't have any alpha hydrogens. So we do still have hydrogens here, but none of them are coming directly off of the alpha carbon, okay? So this cannot form no enolates. So essentially, if we were to react it with this, we would make sure that we'd only have one final product.
So is so an enolate. So esters and aldehydes and ketones form enolates.
Well, they do ionize. I'm trying to remember if if that chapter used the same exact term. Is that chapter 23? Yeah, it plays in. Yep, so they refer to them as ester enolates. So this is just enolate, ester enolates. Any other questions on chapter 18 or a different chapter?
Here's your piece.
I'm coming down to the last few minutes.
Sweetheart. Oh, Jesus.
Can you go over like the location of pi electrons?
Oh,
The
yes.
location of pi electrons?
Yeah,
Like aromatic, non-aromatic, anti-aromatic, or
like they're above and below the ring.
sure.
Like their location.
Let's talk about it in reference to benzene. So how do I want to do this? When I'm just gonna use kind of simplified. Okay, so if we have an atom bonded to another atom, so the first orbitals that are filled are our s orbitals. Okay, and those are kind of seen as spheres. So basically you have kind of two spheres coming together and we have two electrons being shared. Okay, so those are kind of seen as being directly in between. Okay, pi orbitals are dumbbell shaped and there are three different kinds. So we have vertical, we have one that would be coming out of the board and going into the board, and then we have horizontal, okay? So electrons fill all of these orbitals in a progressive fashion. So the ones that we tend to talk about are the ones that are in the vertical p orbitals. So for example, each of these carbons in the benzene ring has electrons in these vertical p orbitals. Now, the electrons are going in this fashion, but they interact with other electrons in other p orbitals. Is any of this making sense?
Yes.
Okay. So when we have something like benzene, we have electrons above and below the ring technically at the same time. Because again, remember, these electrons are constantly flowing. So there's really not a single location. They can be above and below the ring. Okay? So each of these can interact with the other electrons, which is why we refer to it as electron delocalization. Does Does that answer your question? Yeah.
Yeah, what's it called when the clouds above and below the ring versus equatorial?
Axial. Yeah, so that's referring to substituents. So if you have substituents above or below a ring, it's axial. I like to think of an axial skeleton.
So the number of pi electrons in a benzene ring is 6.
It is 6.
So are there pi electrons in a like regular cyclohexane?
Well, let's talk about that. So pi electrons are found in double bonds, right?
Double bonds.
Right? So if we just have single bonds, we only have sigma bonds. So only sigma electrons. So you would have to have a double bond present for the p orbitals to be interacting.
So the hybridization of benzene is sp.
How many hydrogens are coming off of every carbon in a benzene ring?
2.
Benzene ring. 1, right? Because this carbon has 1, 2, 3 bonds already. So there would only be 1 hydrogen coming off. In a cyclohexane, or any cyclo, we would have 2 hydrogens coming off of each carbon. Okay? So if we have 1, so if we're looking at this here, we have 1, 2, 3 attachments. So that's sp2 hybridization.
Okay.
This would be sp3.
sp3. And then there was a question on chapter 25 about oxocyclooctane. If anyone remembers what it was, I don't remember what the question was exactly. It was, dang, what was the question?
I know that was the one that he brought back.
Is that the one that he took back, 25?
Pretty
Yeah.
sure.
Yeah.
I haven't seen it.
Ah, dang it. Okay.
I think he was just asking what it was.
What it was?
Like, I think it
What was
was
the name?
saying to name it. Yeah.
Okay.
Oh, okay.
Never mind then.
Okay.
And that was azocyclooctane. Azocyclo.
Yeah, oh yeah, it was, you just
Oh.
named it.
Okay.
Yeah.
I remember seeing it, I was like, wait. Okay.
Yeah, it's a tougher one because it's larger. Okay.
Ooh, Jesus.
Did that answer your question, Amber? Sorry.
Yeah.
Okay. It's a tough one.
That helped me too, so thank you.
All right. Gonna close it up. Any last questions? All right.